be critical about this issue, about this criteria. So maybe the decision maker to prefer to evaluate the second criteria in a form of 1, 2, 3, 4, 5 linguistic term set. And then the issue of multi-granular is actually the unifying it. Since we give the flexibility to the decision maker to choose how many linguistic term set they are comfortable with, so we have another issue of unifying it. So the process, the difference between homogeneous is the part where the method allow only one single. We choose only a common, that's the word that I'm trying to say, a common linguistic term set for all the decision maker to evaluate each of the alternative, the criteria. But as for heterogeneous, we give the flexibility to the decision maker. Why do we need to give the flexibility to the decision maker actually? I want to, I cannot. Okay, never mind. Why do we need to give the flexibility? It's because of this, the one that I mentioned just now. Due to the cultural, educational background, experience, knowledge, etc. Does it produce in a different opinion on something? For example, let me give you a brief example. Say that my husband and I were trying to buy a new car, for example. And then we have like three alternatives, A, B, and C. So this is decision maker 1. I am the second decision maker. For example, this is, I'm not really buying any car. Just giving you an example. So, okay, where is my 2? Oh, my handwriting. Decision making 2. So we have like 3 options, for example, A, B, and also C. Okay, now let's look at the criteria. What is the criteria of a car that we want to consider before we buying a car? For example, we have 3 criteria to be considered. The first one is in terms of price. The second one maybe of the design of the car. And the third one maybe the performance of the car. So maybe the price, my husband and I agree on having these 3 linguistic term sets. Expensive, neutral, and cheap, for example. Cheap is C. So we agree. We agree that in terms of evaluating the price, we agree on 3 linguistic term sets. Now, how about the design? So the design, maybe my husband is not very keen, not very critical about the design of the car for as long as the performance is good. So maybe the linguistic term set that he agree on is maybe 5 linguistic term set, for example. But meanwhile, on the other hand, I'm very critical of the design of the outer aspect of a car. So I'm critical about this aspect. So maybe I want to have a more details in terms of the linguistic term set. So I choose 7 linguistic term set, for example. Very pretty, good, neutral, and so on up until 7 linguistic term set. Now let's talk about the performance. This is the difference of the agreement on the linguistic term set. For the second criteria is actually because of our preference. I prefer to drive in a very nice car, for example. And the third criteria maybe regarding the performance of the car. So since my husband is an ex-engineer who works at Proton developing the engine of a car, so he has more knowledge, more critical. He is critical about this issue, about the performance of a car. It is very important for him. So maybe he prefer to have a like 10 linguistic term set in evaluating the performance of a car. And for me, for as long as the car is moving, I think that's fine with me. So maybe I prefer to use 2 linguistic term set, for example, good and bad, for example. So due to the difference of all this, we need to undergo one more step that we call unifying. We have to unify everything here in a one form before we can aggregate it. So for heterogeneous, we have additional process. We call it unifying. Homogeneous, once we already evaluate the output, then we can straight away aggregate and then evaluate the output. For heterogeneous, since we already give the flexibility to the decision maker in determining the linguistic term set, then we have to unify it first before we can undergo the aggregation process. So that is the difference between homogeneous and also heterogeneous. Okay, as for literature review, MGL, multi-granular concept, in real world has been discussed in other areas also, such as temporal database, network area, software area, imaging area, and decision-making area. So for this research, we focus on decision-making area lah, that use the concept of multi-granular. Okay, based on J.A. et al. 2015, MGL in decision-making can be divided into 6 categories. The first one is traditional multi-granular based on fuzzy membership. The second one is ordinal multi-granular FMM based on BLTS. This one is actually BLTS. The third one is ordinal multi-granular based on 2 tuple. The fourth one is hierarchical trees. The fifth one is based on qualitative description spaces. And the sixth one is discrete fuzzy numbers. So this research we narrow down on the first category. I'm trying to propose a method for the first category that is based on fuzzy membership. So what is fuzzy membership? So by all means, fuzzy membership, fuzzy set is in a universe discourse X is characterized by a membership mu AX that takes value into the interval from 0 until 1. Before we proceed, let me explain to you on what is fuzzy numbers. Fuzzy numbers is actually we're trying to eliminate the sharpness of the evaluation. Say that is a yes or no. So fuzzy numbers eliminate those sharpness. They give the membership for each of the evaluation. Say that I always claim to, let me give you one example. I'm not serious about the example. I always claim I am a very, very pretty person. Not really, it's just an example. So maybe the decision maker who wants to evaluate whether is it really that person is really beautiful or not. So the decision maker one, we have like three membership, okay, three set of membership, pretty, neutral, and not pretty, for example. So it can be represented into a fuzzy numbers. So say that we select triangular fuzzy numbers. Fuzzy numbers has several types. For example, triangular, trapezoidal, S-Gaussian, and so on. Now, discrete, we have many types. So say that we want to represent the evaluation in the form of triangular fuzzy numbers. So pretty maybe at this point, okay. Natural maybe at the middle of it. Not pretty at the, sorry, the line is not that straight. Okay, let me try and draw this again. So not pretty, maybe the triangle placed at the left-hand side. So when we illustrate it as in one graph, it will become something like this lah. So it will become something like this. It overlaps. The membership overlap of each other. So the sharpness of between yes or no has been eliminated. So that is so that is fuzzy numbers lah. I try to explain in a words that hopefully everyone can understand. And then the membership function can be illustrated in the form of membership function. Say that this one is I said that not pretty, right? This one is natural. This one is pretty. So let's say that pretty is from 0 and this one is 0.1, for example. This one falls in 0.7, for example. This one from 0.0 this one is 0.10, 0.5, for example, and so on lah. So from there, you can see that the category of the evaluation, the evaluation of the criteria, the sharpness has been eliminated because each of them the evaluation has a membership and it overlaps one another lah. So the sharpness has been eliminated. So it's not narrow no more. So say that the decision maker number 1 wants to evaluate, is it really I am that pretty? For example, my husband, he better rank me with very pretty lah. As for my little brother, on the other hand, let's not go there. Maybe he will rank me with not so pretty. Kidding only. Just that one is just a joke. So that is what is fuzzy numbers. So I choose the first category because I want to the sharpness has been eliminated lah basically. That's my point. Okay, as the objective of this research, we want to introduce MGL in decision-making method and then give decision maker the flexibility to choose the linguistic term set. They have the flexibility. And then we want to implement the introduced MGL to a secondary data to validate the proposed method. Is it accordingly or not? So that is the third objective. So for methodology and result, the improved and the improved MGL that we are trying to propose, we call it SMM, a simplified MGL method. So this process undergoes this undergoes certain process. The first one is unifying, the one that I mentioned just now. Before we can aggregate the evaluation that each of the decision maker gave, we need to unify it first. We have to change the form of linguistic term set in one form before we can proceed to the aggregation process. So unifying process, okay, the basic of it actually taken from F. Herrera, where we select the labels based on these two requirements, the maximum labels among all, to lessen the complexity index. If exists more than 2 maximum labels, we choose the greater number of membership function. Say that we have triangular and trapezoidal, we choose triangle because of the, we choose trapezoidal because of the greater number of membership function. So let me explain to you what does it mean by these two. Okay, say that, for example, okay, let's check back to our example just now, the car, the choosing of a car just now. Say that the first, sorry, I need to remove this. Okay, the first criteria, the linguistic term set that we choose is 3, right? So this is the common, meaning that we agree on this. And then this one is 3, this one is 3, and then this 7, this one, the design just now, maybe 3 also, for example, maybe 3, this one also 3, this one is 10, this one is 2. So what is the most common number of the linguistic term set? 3, right? So we're going to convert everything in a form of 3 linguistic term set before we can aggregate it. Because why? Because we want to less the calculation involved. To transform all this, there is calculation involved. So since there is 3 times agreement on the selection of the multi-granular linguistic term set, so why not we choose the most common? So that is what it means by these two parts. Later on, I will explain to you why we want to lessen the complexity calculation of it. So actually, the unification process explained here, we use the concept of ratio. We use the concept of ratio in order to find the common linguistic term set before we can unify it. This is the formula. No? And then once everything already unified, we proceed with the aggregation process. So the aggregation process is based on C.T. Chen Lin Huang 2006, where their method is actually only involve less calculation. Why? Again, later on I will explain to you why. Because the aggregation for fuzzy numbers, in order to aggregate the evaluation, there is an operation for fuzzy numbers lah. But based on Chen Lin and Huang, they propose an aggregator which is involve less steps to be taken. Meaning the first item here and the last one, we don't need to find the aggregation process. We just find the minimum value and also the maximum. So by all means, this will reduce the calculation involved lah. That's why we choose Chen Lin and Huang method. And then for evaluation process, we use Xing Min Chen and Sang Guan 2011 because their method is actually based on area based. In evaluating fuzzy numbers, there are a lot of methods to choose on. We can choose dominance method, and then we can choose spread method, and then we have area, we have AHP, we have top 6, we have a lot of method to choose on. But for this research, we choose on area because of the consideration. Because they consider the fuzzy number as a whole. We consider everything consists of the fuzzy numbers. So by doing this, hopefully the information will not be lost. There is no loss of information. And why another reason why we choose this method is actually the original of the evaluation that we take in the fuzzy numbers, right? It is up until the final stage of evaluation, meaning up until the final stage, then we convert it into a scoring one, meaning we kept the fuzzy number in the original form, up until final, we want to evaluate, then we change the form of the original one. So that's why, not that's why. So hopefully by doing that, by selecting this, the loss of information that stored in the original form of our evaluation is not been lost lah. It will keep as it is. So loss of information will be reduced. So this is actually just the summary of the process. We call this method as SMM lah, a simplified multi-granular method. So now let's proceed to the next slide. Okay, we're done. I'm done explaining this a bit. And then we have, we want to validate the method. We want to validate the method based on a case study based on F. Herrera. So this method has been used by several other researchers also. Okay, they want to validate their proposed method, they use this one. So based on our method, okay, the secondary data is actually based on, it talks about an investment company where they want to invest a sum of money in the best option there is. So there is a four alternatives to choose from: car industry, food company, computer company, army industry, and they have 4 decision makers to evaluate the alternative. Okay, they have risk analysis department, growth analysis department, social political analysis department, environmental impact analysis department. So all the decision maker will evaluate each of the alternative, and then based on their preference of the cardinality, the linguistic term set. We have set A with 8 there, set B 6, set C 4, set D 8, and so on. This one, what's the difference between set A and D? Actually, this one is in the form of triangular. This one is in the form of trapezoidal. So we have 4 terms there. Okay, for triangle we have 3. So that's the difference. So based on their opinion, based on their preference, their knowledge, their background of studies, their experience, and so on. So they will decide, and then they decide which label of set to be used, and then they evaluate each of the alternative. The expert will evaluate each of the alternative. Then this will undergo the process of unifying, and then we will aggregate it. Where is the aggregation process? Somewhere here. Well, yeah, this is the aggregation process. And then lastly, we will evaluate it based on the method that we choose just now lah. So based on the result that we get, okay, comparing with 3 other methods, SMM is our proposed method. This is SMM. We managed to get the result similar to others with the low complexity level. So CI and also RCI is actually complexity index, relative complexity index. They are talking about the complexity level of the method, the SMM method, the first, second, and third method. So we compare. SMM managed to get this the less value for the RCI compared to other 3 methods. So why is it important for us to reduce the complexity of a method? Why? Because complexity imposes a high degree of uncertainty, it is time consuming, low level of accuracy may occur, and the efficiency of the result is uncertain due to the complexness of the calculation. So that's why we are trying to propose a method with a less complexity level. So again, these 2 methods is actually taken from Harliza et al. Basically. So okay, this one is just explaining on this RCI. It is taken from this method. So as for conclusion, a less complex method in MGL term-based method is introduced. This one is introduced for true for the first category only. The one that I mentioned just now, we have 6. This one is true for the first category because we are comparing between its category only. Others we are not going into that just yet. And then a decision-making problem is implemented using the multi-granular linguistic type, and so linguistic term set. Sorry about that. So this is just the validating. And then the complexity index of the proposed MGL is compact. We calculate the complexity level of each method, and then we compare. And then we can conclude that the proposed method has a lower complexity index. That one is another story, another subchapter for this lah. And then for recommendation for future work, among the proposal is we may want to consider the confidence level of the decision maker and also the degrees of optimism of the decision maker. Meaning that sometimes in evaluating something, we are not very confident. For example, the car just now, the example of a car, I want to evaluate the performance of the car. When I rate this one as good, actually I'm not very confident. Maybe my confidence level in between 0 to 1, for example, is only 0.5. I am 50% confident in evaluating that. So we may want to consider in future the confidence level. How to incorporate this one, we need to have to further investigation. Or maybe we want to consider the degree of optimism of the decision maker. Whether the decision maker is pessimist or optimistic about the evaluation they are making, about the problem. We may want to consider this in future maybe. And then a lower relative complexity index in other categories. Maybe we want to extend that. We have another 5 categories, right? We have based on BLTS, two-tuple, hierarchical, qualitative, and also discrete. Maybe in future we want to propose a less complexity level for this category. Maybe. And then what else? Among the consideration are weight of criteria and also expert. Okay, what does it mean by the weight of the criteria? Okay, let's go back again to the example of a car just now. Okay, maybe about the car. Where is the example of the car? Decision maker one is my husband. So he's paying for the car. So maybe he have more weightage on the decision. So maybe he has a weight of 0.7. Only have 0.3, but how to incorporate? We have to more investigation to need to be made lah. We have references in other methods, so maybe we can refer to that. And also the weightage of each of the criteria in terms of price. Maybe the criteria for the price is very crucial. We are very concerning about the price. So maybe the weight for the price is 0.4. Design and performance of the car equally important. So maybe 0.3, 0.3. So that is among the future work that can be incorporated in our method for now. And then creating programming model with this one we need an expertise of the program. Maybe we can come up with the programming, we insert the rules and such, and then we all we have to do in order to get an output, we put in the value of the evaluation, and then voila, settle with the output. Maybe in future recommendation. And then that's it from me. So, but before I end my presentation, if there is any collaboration opportunities or anything you want to ask, you want to comment, you may do so by contacting me via my email harliza50@uitm.edu.my. I am open for this. That's all for me. Thank you.
All right. Thank you, Dr. Harliza, Muhammad Hanif, for an interesting topic and your valuable insights. Now for Q&A sessions. Has anyone have question regarding the topic that has been presented just now by Dr. Harliza Muhammad Hanif? Question, anyone?
May I ask a question, please?
Yes, yes, Prof.
Assalamu alaikum, everyone. In fact, I wonder which area of mathematics more important in your research? Say, mathematics has, say, different branches, algebra, mathematical analysis, functional analysis, probability theory, or numerical analysis, etc., etc. So, which area should focus on student to start with your research?
Okay, for this area, it actually falls under the applied mathematics. To be more critical about it, it's about fuzzy numbers, Prof. The main area is actually fuzzy numbers, and then we.
No, in fact, fuzzy numbers. Before fuzzy theory, it was not given such kind of theory, right? or just, I mean, if you say, if you just remove fuzzy, so no such kind of research what you are doing. Am I right?
I'm sorry, Prof. I'm not following.
No. I mean, this your research is fully fuzzy theory.
Yes.
Without fuzzy theory, you cannot do it.
Yeah. Fuzzy is a part of the
Because
research.
numbers are there, functions are there, everything is there.
Yes.
Maybe some equations you can solve, still can do without fuzzy. So if you remove fuzzy, is it possible to do such kind of research?
Yes, I think yes.
Because students say, let's say students, some student wants to go to your area. So what kind of mathematics he should do or she should do focus on?
Without fuzzy, is it, Prof?
No,
Besides
say
fuzzy.
without fuzzy, yeah. No. In general, your recommendation for students to come to you to do research together.
If beside fuzzy, maybe other areas can also be implemented, but I need to dig more info into that, Prof. As for now, I have no idea. But it is possible actually, Prof. Without fuzzy.
Okay. Thank you.
Okay, anyone else? By the way, Dr. Harliza, I think I have one question. Can you go back to your, I think step 4? Step 4, you are saying that there are many methods that can be used, right? For step 4, to get step 4.
The evaluation process, is it, Doctor?
Yes.
Yes.
Okay. There are many methods to be can be used, right?
Yes, true.
Okay. If you were to select one method, what kind of criteria that you look that specific method, and why does that method chosen rather than other methods? What kind? What type of?
For the research, I prefer on using the area-based method because of the consideration of the evaluation. They considered the area under of the fuzzy numbers. We considered the area as a whole, meaning that the evaluation is being evaluated based on the whole fuzzy numbers there. That's why besides, there's also other methods such as spread. Spread is talking about the spread of the fuzzy numbers. So it's limited in evaluating the output by the spread only. For example, not necessarily that spread is not good because my master research also based on spread. It's just that for this research, I choose area based because of the consideration of the output as a whole. Dominance also actually is a good area to explore, to be explored lah in evaluation process. Maybe in future recommendation, we can look into other method also with another advantages, perhaps.
Oh, okay. So you are saying that those results different from different methods give a distinguished result or more approximately result?
Supposedly they will give the same result. If different, there must be a reason for it lah.
I see. Okay. Anyone else? Okay, I think that's all, Dr. Harliza. Thank you very much for your presentation. Thank you.
Thank you. Thank you
Thank
all.
you. Okay. Okay, next, we move on to our next presenter, which is Dr. T. Kamaraj. He is an assistant professor from Department of Mathematics, Satyabama Institute of Science and Technology, Chennai. In in the year of 2000, he obtained his Master of Science and Master of Philosophy in Mathematics from Loyola College, Chennai. Then after that, he got his PhD in Mathematics from Satyabama University, Chennai in 2015. Where the title of his thesis is Certain Study on Two-Dimensional Pictures and Automata. So please welcome Dr. T. Kamaraj to present his topic, which entitled Graph Labeling Based on Some Special Number. Dr. Kamaraj, you have been given 30 minutes of presentation and 10 minutes. Dr. Kamaraj, are you there?
Yes, madam. Am I audible? Am I audible?
I cannot hear your voice. It is
Yeah.
a little bit slow.
Is it audible now?
Can you volume up your
Yeah, I'll just check it
voice?
first. It's in full volume only, it is showing. Still, it's not audible?
Cannot hear Dr. Kamaraj?
Yeah, I can hear you. I can hear you. Can you
Yeah,
hear me?
but we cannot hear you actually. It is the volume is too
Okay, let me check.
slow.
Am I audible now? Am I
Hello?
audible? Hello, am I audible? Yeah, I just check once, okay?
Dr. Kamaraj, I think we can hear you.
Yeah.
Yes.
Am I audible to you? Yeah, am I audible now? Am I audible to you?
Yes, Dr. Kamaraj, you can proceed now.
Yeah, am I audible now?
Yes. You can share your slide. You can share your slide.
Sure. Is it visible now? Yeah, is it visible? Slide is visible?
Yes, we can see your slide now. You can proceed the presentation, Doctor.
Okay. Yeah. Hello, good afternoon to everyone. I'm Dr. T. Kamaraj, an assistant professor, Department of Mathematics from Satyabama Institute of Science and Technology, Chennai, India. I'm working in the field of graph theory, the labeling, as well as the domination part. Currently, I'm guiding 4 students in my research field. This is one of the works we have done so far with one of the candidate, PhD candidate, Mrs. Neetu. So today's session, we are going to discuss graph labeling based on some special numbers. So graph labeling, it is an assignment of labels. Labels means some elements of some set to the elements of a graph. Normally the elements of graph may be points and edges. So it may be assignment of labels to points or edges or both. Depends on some conditions. Okay. So we discuss graph labeling using some special numbers which are represented by legendaries and Jacobi symbols as well as M zoom color numbers. Here in our discussion, we consider path and wheel related graphs, and if possible time permits, we also see some operations on those graphs, how we can go for labeling using the special numbers. So all these graphs under our discussion will be a finite, simple, undirected graph, and we follow the basic notation and terminology of graph theory as in Harare and graph labeling as in Gallian textbook. Now, graph labeling was introduced in the year 1967 by Alexander Rosa. The labeled graphs find many interesting applications in science and engineering and technology. Graph labeling has a wide range of applications in circuits design, X-ray crystallography, coding theory, radar, astronomy, communication network design. Now, our objective for this today's discussion to label a graph by some number theoretical concepts. One of the concepts what we are going to use quadratic residues, and motivated by this legendary symbols and Jacobi symbols, and the other kind of numbers we are going to use M zoom color numbers. In the year 2015, such a quadratic residue kind of graphs discussion have started, and the Angusman Das has initiated quadratic residue Cayley graphs. It is represented by gamma n modulo n, where n is a product of two distinct primes p and q. And later in the year 2017, M. Raza introduced quadratic residue graph modulo n, but he has used only the labeling of vertices only. He didn't use the labeling of edges. So in this Razai's paper, the two adjacent vertices have a feature that a square should be congruent to b square under modulo n. So where a and b are the labels of the vertices. So when we have an edge between the two vertices, if this condition is satisfied, a square equal to b square under modulo n, where a and b are the labels of the vertices. So now we are interested in working on a similar kind of labeling, but both for vertices as well as edges. So here we are going to consider a labeling called square residue labeling that is motivated by the quadratic residue. So let me formally define what is quadratic residue in number theory. First of all, I will come from the number theory. So when you say an integer is a quadratic residue under modulo p, if this equation, you can see in the screen, the equation 1 I made, if that equation x square is congruent to q under modulo p, has some integer solution x, then we can say that q is a quadratic residue modulo p, where p is a positive integer and q is an integer between 0 to p. Normally q will not assume as 0. So if the congruence equation 1 is not having any solution, then we say that number q is quadratic non-residue under modulo p. Examples. So let me start with some examples so that you can understand this quadratic residue concept. So you all can understand 7 square. Okay, so 7 square is 49. Under modulo 10, the residue is 9. So now, since it is 9 is congruent to a square of the number, so this 9 is called as quadratic residue under modulo 10. Okay, but you can also see that 3 square also 9, and that also congruent to a square number. So in anyway, 9 is a quadratic residue under modulo 10. Now, in fact, for modulo 10, the entire set of quadratic residues are 1, 4, 5, 6, and 9. So you can see the explanation in the screen. Now, based on this quadratic residue concept, we are going to define some symbol. In fact, something a function like that, even though the name is symbol, but actually it is a function. Suppose if you consider a prime number odd prime, okay, if you consider an odd prime number p and q a non-zero number q, we can define a legendary symbol denoted by q divided by p as follows. the q divided by p value is 1 if q is the quadratic residue of p. That means the numerator q is a quadratic residue of the denominator, okay? And if q is a quadratic non-residue of p, then the value of this legendary symbol is -1. So that means what? Legendary symbol always will give you either +1 or -1 based on the nature of the quadratic residue of the numerator. If the numerator is a quadratic residue of the denominator, then the value of the legendary symbol is 1, otherwise its value is -1. For example, if you consider the p value as 13, and let me consider the quadratic residues of p, okay? So we can easily compute the quadratic residue of number 13 are 1, 3, 4, 9, 10 and 12. And the non-quadratic residues of 13 are 2, 5, 6, 7, 8 and 9. And as per the definition of legendary symbol, in the previous slide what we have seen, if the numerator is a quadratic residue of the denominator, then the value of the legendary symbol is 1, otherwise it's -1. So according to that, for the first row, first set of numbers 1, 3, 4, 9, 10, 12, which are quadratic residues, no? So when you go for the legendary symbol for those numbers as numerator and denominator as 13, the answer is 1. And for non-quadratic residues, those numbers as a numerator and the 13 as a denominator, then since it is a non-quadratic residue, the legendary symbol value is -1. And as a generalization of legendary symbol, we have also got another symbol called the Jacobi symbol. In fact, in the legendary symbol definition, you can see that there is a restriction in the denominator. The denominator p is an odd prime number. But in Jacobi symbol, it is not the case. Here, p be any positive odd integer. But it is an odd integer, but need not be prime. So p be any positive odd integer with the prime factorization we have, okay? So the denominator p is any positive odd integer. Now in that case, a similar concept like a legendary symbol we can also discuss for Jacobi. The Jacobi symbol of q divided by p is defined for any q by this equation. Now q divided by p, for this the Jacobi symbol is providing what value means. It is a product of all the legendary symbols whose numerator is q and denominator is the prime factorization of the capital P. You can see that capital P in the first line. Here P is a product of primes, in fact prime factorization. So if you have such a prime factorization, then for each of these primes, what are the split up primes here? PAs. So for each of these prime as a denominator and q as a numerator, you can have a legendary symbol value. You know, legendary symbol gives either +1 or -1, depends on the q, whether it is a quadratic residue or not quadratic residue. And after this, we have to work it out this product, and this product again will give you either +1 or -1. So ultimately, Jacobi symbol also give rise to the value either +1 or -1. But it is a generalization of the legendary symbol where the denominator need not be a odd prime number. Okay. And some properties of these Jacobi symbol or legendary symbol. So it depends on the context. If the denominator is odd integer, means it is that result will be pertaining to the Jacobi symbol, and if the denominator is odd prime number, then that result will be pertaining to legendary symbol. So one of the interesting result here, this one. So here, whenever A is congruent to B under mod P, then A, that is the legendary or Jacobi symbol of A with the P is same as the Jacobi symbol of B with P. One simple example, what we can say, for example, if you go for 7, okay, so 7 under modulo 3, okay, so 7 is under modulo 3, so if the value is 1, okay, so that means what, now we can say this result is 7 by 3 is, that is the Jacobi symbol value of 7 by 3 is equal to the Jacobi symbol of, is equal to, according to this result, Jacobi symbol of 1 by 3, okay. Jacobi symbol of 1 divided by 3 by this result. This bracket stands for Jacobi symbol. So according to this property, we can say that 7 by 3 is same as 1 by 3. So that means what? This Jacobi symbol we can discuss only for those numerators which are lesser than the denominators. So this result clearly says what? We can study about the Jacobi symbols, or we can just we can work it on the Jacobi symbol only for the numerator which are lesser than the denominator by this result. Okay. And some of the results, AB by P will be equal to the Jacobi symbol of A by P and the Jacobi symbol of B by P. Okay. So like this we have. So now we are now going to define a graph labeling based on this Jacobi symbol. You know, Jacobi symbol and as well as legend symbol, all are derived from the concept of quadratic residue concept. Now let me see the labeling definition. A graph G is said to have a square residue labeling. Our labeling we are calling by a name what? Square residue labeling. If there exists a bijective mapping from the set of vertices V to the set of odd numbers 1, 3, 5, 7 up to 2k minus 1, where k is the cardinality of the vertex set. That means if suppose there are 10 vertices are there in the graph, then here the numbers are 1, 3, 5 up to 2 into 10 minus 1, that is 19. Okay. So such that whenever there is an edge between x and y, where x and y are vertices, here x and y are what? Vertices. Then the label of the vertex that we call by FV of x and FV of y are relatively prime. You know, relatively prime means the GCD is 1. Okay, greatest common divisor of those numbers is 1. And edges are labeled with an induced function FE, which is defined as that FE connecting, that is the label of the edge connecting x and y. Okay, so x is a vertex, y is a vertex, and the label of this edge we calling by FE of x, y. So this FE of x, y is given by the Jacobi symbol of x divided by y. So each edge label is given by the Jacobi symbol only, and you know Jacobi symbol always have the value either 1 or minus 1. So it depends on the Jacobi symbol values. Okay, it depends on whether the numerator is a quadratic residue of the denominator, okay, or not. And not only this labeling, but it has some restriction. Okay, so that we cannot be able to freely assign the labels for every edge like this. But also we have to consider one more restriction in this labeling. What is that? The positive difference here. The positive difference between E1 and E minus 1. Where what is that positive difference only I am calling as D of E1 comma E minus 1. What is that E1 E minus 1 stands for here? E1 denotes the number of edges with the label 1, and E minus 1 denotes the number of edges with the label minus 1. So when you consider the, when you calculate the number of edges with the label 1 and the number of edges with the label minus 1, and if you take the positive difference, that answer cannot be more than 2. It should be less than or equal to 2. Okay. So if this, with this condition, if we label the vertices and edges, then we call that labeling as what? Square residue labeling, and the corresponding graph which admits such a labeling, we are calling a square residue graph. So now one of the results what we had derived, in fact it's not already presented, it is one of the results what we had derived in the case of Jacobi symbol. Jacobi symbol for p by p plus 2 value is 1 whenever p takes 8n minus 1 or 8n minus 7, where n is 1, 2, 3, etc. Similarly, minus 1 whenever p takes the form 8n minus 3 or 8n minus 5 whenever n equal to 1, 2, 3. And before going to our discussion of some examples on the residue labeling, square residue labeling on the graph, let me consider some simple definition of some of the graphs, like path graph. You all know path graph is a sequence of vertices and edges, where the graph has only 2 vertices of degree 1, and the remaining all the vertices are having degree 2, where degree is the number of edges incident on the vertex. So cycle graph, you know, it is a closed path graph like that, and a wheel graph, So wheel graph is obtained by connecting a single vertex to all other vertices in the cycle graph. So you have a cycle graph. You have a cycle graph. So it has, for example, it has 4 vertices. Okay. And now join each of these four vertices to other vertex. So this kind of graph we are calling is what? You have a cycle graph and it has 4 vertices. And join the central vertex to all these 4 vertices. So this is what wheel graph we are calling. And it has 2n minus 2 edges if the wheel graph has n vertices. Okay. So one of the results what you identified, every path graph on n vertices where the n is greater than or equal to 3 is a square residue graph. That means what? Every path graph on at least 3 vertices will admit the square residue labeling for this vertices and edges. I don't want to discuss the proof of this result. Let I illustrate this result using some example. You can see the first diagram what I have given is it's a path graph on 4 vertices. Here I can label the vertices as starting from the odd numbers 1, 3, okay, 1, 3, 5, 7, like that, okay, and the edges are labeled with either 1 or minus 1 corresponding to the Jacobi's function. That is here among 1 and 3, which is a small number here? 1. So I'll put that 1 in the numerator and 3 in the denominator. Okay, can you one of them tell me, is that the 1 is quadratic residue of 3? That means can you write 1 is congruent to some x square under modulo 3? This is my question. Under modulo 3. Can you write 1 as congruent to some square of some number under modulo 3? Definitely. Where x square we can write 1 square itself. What is the solution? One of the solution? X equal to 1. So similarly, so that means it is a quadratic residue. 1 is a quadratic residue because we can write 1 as congruent to x square. No. So it is a quadratic residue of 3. So that means the edge label should be plus 1. If it is a quadratic residue means plus 1. Okay. And now you see 3 and 5. Okay. So which is a small number here? 3. And which is a larger number? 5. Okay. Can you now write 3 as congruent to some x square under modulo 5? Can anyone answer for this? Can you write 3 as congruent to some x square under modulo 5? Then what is the x value? Can I have some message, or can you mute? Somebody can unmute and tell me. Is it possible such an integer? You can start with I'll give one technique. You start with the 1. Okay. Put x equal to 1. 1 square. Is it 1 square is congruent with 3 under modulo 5? No. Next, put x equal to 2. 2 square. 4. Is it 4 is under modulo? What is 4 under modulo 5? The answer is 4. Okay. And then 3. 3 square. 9. 9 under modulo 5 is 4. And 4. 4 square 16 under modulo 5 is 1. That's it. So that means we cannot have an x satisfying this equation. That means 3 is not a what? Quadratic residue of 5. So if it is 3 is not a quadratic residue of 5, then the label is minus 1. Okay, similarly you can see that 5 is not a quadratic residue of 7, so the label is minus 1. If you do this, also you have to check it out what? The one more condition what I mentioned in the previous occasion, what is that? The number of edges with the label 1 and the number of edges with label minus 1. Okay, if you take the count and take the positive difference, that should be lesser than or equal to 2. So here in our case, how many edges are with the label 1? 1 edge. How many edges are with label minus 1? 2 edges. So what is the positive difference between 2 and 1? The difference between positive difference between, take the modulus. Modulus of 1 minus 2. What is that? 1. So this is less than or equal to 2. So our condition is satisfying. So that means what? The path graph on which here 4 vertices. the path graph on 4 vertices satisfies all the conditions of the square residue labeling. That means it admits the square residue labeling. So we can say P4 is a square residue. Similarly, for any other path graph on n vertices where n is greater than or equal to 3, you can have what? A square residue labeling. Similarly, for a wheel graph, this is a wheel graph. Okay, so a very similar discussion you can have. But in wheel graph, you see that the central vertex, you see that central vertex. What is that central vertex here? So what are the options? So you see totally how many vertices here? 6, 3 plus 3, 6 vertices. Okay, so 6 vertices, and so 6 vertices. And the central vertex, you see that central vertex is adjacent to all the remaining 5 vertices. You can see that central vertex is adjacent to all the remaining vertices. Okay. Now, as per the definition of the quadratic residue labeling, I can have only the co-prime numbers as a labels for the adjacent vertices. Do you get? I can assign what? Only co-prime numbers are the, what is that? Is a number whose numbers whose common greatest common divisor is 1. Okay, so who co-prime numbers, that alone we can assign. So that means what? Suppose if I assign for this vertex, the assign value is 1. Suppose if I assign value is 1, then I can assign here. Here in this diagram it is assigned 7 actually. So 7. But suppose if you assign 1, I can assign here 3. I can assign here 5, 7, okay, 9 and 11 like this. Okay. Now in this case, you see that 1 is, what is it? Look at this edge. This edge connecting, what are the 2 vertices? The labels 1 and 7. Here, what is the Jacobi symbol of 1 and 7? What's the answer? Is it 1 is a quadratic residue of 7? Yes or no? 1 is a quadratic residue of 7? Yes. So that means I'll have the values 1, the edge value is 1. Like that, 1 is a quadratic residue of all other remaining numbers. 1 is quadratic residue of 3, 5, 7, 9, 11. That means for each edge I have to assign the label as what? 1. Then how many edges are labeled with 1 here? At least I have what? 1, 2, 3, 4, 5. Okay. And since I have labeled 1, 3, 5 here, it's not the direction I'm just showing, it is a rim edges I'm showing. So here also 1 is a quadratic residue of 3, okay. So if you totally take the count of number of positive, number of edges with the label as with the label as 1 and number of edges with the label as -1, the difference between the E1 minus E minus 1 is exceeding 2. Is exceeding what? 2. So that means here we cannot be able to freely assign a central vertex as 1 or 3. That we have to carefully analyze and do it. I have provided one algorithm also. In the algorithm is in the paper. It's in the time constraint. I didn't show here. So if you follow that algorithm, you can get the exact value of the central vertex. Here the central vertex is a key point. So here in our case 7, I have assigned as a 7. And after this what? I can now you check this. How many edges are with the labels as 1 and -1? You can see easily check that, and the difference between the number of edges with 1 and number of edges with -1, the positive difference between them is not exceeding 2. So that means wheel graph on n vertices obeys or admits square residue labels. Okay. Shall I get the timings one? Still, how much time I have? Shall I get the timing from you? Yeah, still we have some time. Can you? Yeah, I'll proceed. Yeah, somebody is raising your hands. Shall I? Yeah. Okay. I don't know how to answer here because I'm in the full screen mode. Okay, so let I answer at the last 10 minutes. First, I'll complete my other part of the presentation. Okay. So now this is the illustration I showed in the wheel graph. What I shown explained here, that what I have given in the next slide also. So here I have mentioned that not only 1, even I can't assign 1, 5 or 11 also for the central vertex. for this central vertex, I can't even assign what 5 or 11. So only the 7 is the only possibility here. Okay. Okay. So our next concept of special numbers is zoom color numbers. So zoom color, a mathematician in the year 2003 had generalized the concept of perfect numbers and published a sequence of positive integers in the journal Sloan's A083207 integer sequence, which is known later as zoom color numbers. Okay, so the zoom color number, actually, what is a zoom color number? A number n. Okay, if it is a positive integer with the property that positive factors of n can be partitioned into two parts such that the sum of the two parts are equal. Okay, such that sum of the two parts are equal. Okay, so we have, for example, 5. Okay, so So 6, let us say. Okay, so what are the positive divisors for the 6? 1, 2, 3, 6. Okay. So now what it says, a zoom color number, if you are able to partition the numbers, okay. So if the partition is suppose 2 plus, here suppose 2 and 3 are considering, okay. That means suppose one partition is 1, 2, 3. And the other partition is 6. Okay. Okay, so now what is the first partition numbers? 1, 2, 3. If you add all these numbers, you are getting the answer as what? 6. And what's the other partition? It is involving just 6 only, so we have the number as 6. So now that means what? It is satisfying this condition what? So if we have a partition of 2 sets and some of the numbers in both the sets are equal. So then 6 is called what? Zoom color number. 6 is one of the zoom color number. Okay. In the year 2013, Dr. Bala Murugan and Thirisangu and Dr. K.G. Thomas introduced zoom color labeling algorithms for complete bipartite graphs and wheel graphs, full binary trees, and square grids. In the year 2020, Harish Potadia and Helen Saikia established M zoom color labeling for non-totally disconnected graph. Let me see what is M zoom color labeling in the next slide. A positive integer n is called M zoom color number if the positive divisors of n can be partitioned into two disjoint subsets of equal product. See, earlier in the starting version of the zoom color numbers, what here the example what I said 6. So here I can partition the divisors of the 6. What are the divisors of the 6? 1, 2, 3, 6. That I can partition into two sets such that what? If you add the elements in the two sets, the same answer only we are getting. Now, here M zoom color is if you multiply the numbers in each of the partition, you will get the same answer. So instead of addition, what? Multiplying. So if you multiply the numbers in each of the partition, you will get the same answer. I think the same 6 serves for both the purpose. So what are the divisors of 6? Positive divisors of 6? 1, 2, yeah, 1, 2, 3, 6. Now I can have a partition like 1, 2, 3. One, 2, 3, and the other partition is 6. Now multiply the first partition numbers 1 into 2 into 3, 6. And in the second partition we have only one number, so again 6. So now it is equal. Okay, so now 6 is also a M zoom color number. Not only it is a zoom color number, it is also a special zoom color number. What do you call? M zoom color number. M stands for multiplication. Here M denotes what? Multiplication. Okay. And some of the properties of the zoom color numbers is listed out here. If a positive integer n is a M zoom color number, then the number of positive divisors of n that we denote by tau of n is always greater than or equal to 4. Okay, so even you can see that in the previous example, how many divisors positive divisors of 6, 4. So whenever if a number is a m Zumkeller number, then the number of positive divisors will be what? Greater than or equal to 4. Not only that, even if a number n is, look at the second property here, look at the second property. If the n is a product of distinct primes, like a p8 power alpha I, like that, and suppose if the number n is a m Zumkeller number, then it satisfies the property that what? The number 4 divides alpha I into tau of n. What is tau of n? Number of positive divisors of n. So 4 is the divisor of this product. Okay. So where I is 1, 2, and if the product involves all are distinct primes, okay, all are distinct primes, and the product involves at least 2 distinct primes, then definitely m is a that number is a Zumkeller number. Here in our case, lastly we have discussed 6, no? 6 is actually written as what? Product of 2 distinct primes. What is that? 2 into 3. Now, as per the property 3, 6 is always a Zumkeller number. Okay, so we have some properties also there. Now, the first few m Zumkeller numbers in the numbers, so in the positive integers. So our first Zumkeller number itself was 6. Next Zumkeller number in the set of all positive integers is 8, 10, 14, 15, 16, 26, and keep on going. Okay. I'll illustrate some of the properties what I said in the previous occasion, in the previous slide, in this for the Zumkeller number 24. Now 24 is the Zumkeller number, okay, that we can easily verify. What are the positive divisors of 24? 1, 2, 3, 4, 6, 8, 12, 24. Now these divisors of 24 can be partitioned into 2 disjoint subsets, 1, 2, 12, 24. The other one is what? 3, 4, 6, 8. And if you multiply the numbers in each of this set, the answer is 576. Okay, so both of them are equal. You can easily check it. Okay, hence the 24 is a m Zumkeller number. Okay, now how many positive divisors are there in the 24? Here actually what 8 I already listed out, but there is a way to calculate also. Suppose if a 24, if I write as 2 cube into 3, because 8 into 3 is 2 cube into 3, then what are the prime numbers at the base? We have 2 and 3. Now for each of these prime numbers, see the powers. What's the first prime number is 2. What's the power number here? 3. So add one number to that power number, 3 plus 1. Then what is the next prime number here? 3. What is the power of 3 here? 1. Add that power to 1. So every time what I am doing, I am adding 1 to the power of the prime number. Okay, so 3 plus 1 is 4. 4 into 2, 8. You see that? We already have how many positive divisors? 8 positive divisors. So can you one of them tell me what is the number of positive divisors for 22? Number of positive divisors for the 22 using this approach. So 22 we can write what? 2 into 11. So now you see that 2 power is what? 1. So add 1 to this, 1 plus 1. And what is 11 power? 11 power also 1. Again 1 plus 1. So 1 plus 1, 2, 2 into 2, 4. So for 22, how many positive divisors we have? 4 positive divisors. Okay. Now we come to our labeling of the graph using the m Zumkeller numbers. So m Zumkeller labeling is again pertaining to an undirected graph with the number of vertices as capital modulus of capital V and number of edges as modulus of capital V. Now, when you say we have a m Zumkeller labeling for a graph, a one-to-one function which is taking the domain as the vertex set to set of positive integers is said to be an m Zumkeller labeling of the graph G if the induced function f star e, that is f star is an induced function on the set of edges. See, f is a function for set of, it is the function from the set of vertices to the integers. F star is an induced function from the set of edges to the set of positive integers. The induced function f star of xy, it will give the answer as the product of the labels of the adjacent vertices. So the each edge, suppose x and y are the two vertices and the edges connecting s and y. Then what is the label of this f? The label of this edge? F of x into f of y. where what is f of x? F of x is the label of x. And what is f of y? It is a label of y. So the label of h is nothing but the product of the labels of the adjacent vertices. Okay, like this we have, but this product should be an m Zumkeller number. Otherwise, we can't say it's a m Zumkeller labeling. Okay, so as a product, what number we are getting, this f of x into f of y, that answer should be an m Zumkeller number. Then we call this labeling itself as a m Zumkeller labeling, and the graph which admits such a labeling we are calling as what? M Zumkeller graph. Before going to our some discussion on results on this m Zumkeller labeling, I just introduce some of the simple graphs like path-like graphs and wheel-like graph. Twig graph, one of the graph what we are calling as twig graph. Twig graph is something like, just draw the picture here. We have a path, suppose path containing 4 vertices. Okay, V1, V2, V3, V4. Except the end vertices. What are the end vertices? V1 and V4. Except the end vertices, the remaining vertices you join with 2 more vertices. You join with 2 more vertices. Now it looks like a twig of a leaf, no? Twig of a tree, no? Okay. So something such a graph we are calling as what? Twig graph. And hem graph, it is obtained from the wheel graph. So this hem graph, you know, wheel graph, there is a central vertex and it is attached to some of the vertices, and those vertices are connected by the rim edges. Now you extend these rim vertices. Rim means the vertices at the circumference. So you extend this rim vertices and join to another vertex. Such a graph we are calling as what? Hem graph. So hem graph is an extension of wheel graph where the circumference vertices are extended to some other extended and joined to some other vertices. So such a graph we are calling as hem graph. Now you see that we have made a m Zumkeller labeling of a twig graph containing 7 vertices in the path. Okay. So here you see that the labels how we are assigned. I just give one simple example. For example, I start with the label what here. Here this for this vertex I start with the label 2 into 3. It's not 2.3, 2 into 3. Okay. My label for this vertex is what? 2 into 3. And my label for this vertex I am choosing is what? 2 into 5. Okay. Now, what will be the label for the edge connecting these 2 vertices as per the definition of the m Zumkeller labeling? The product of the labels of the adjacent vertices. So what is the label of this vertex? 2 into 3. What is the label of this vertex? 2 into 5. Just multiply these 2 numbers. 2 square into 3 into 5. 2 square into 3 into 5. Now, whether this number is an m Zumkeller number, how do I identify that? We can use the property. What is that? One of the property of the m Zumkeller numbers is, if the number is a product of primes, then 4 will divide one of the property. I just recall. You see that, look at this second property. 4 will divide the number of divisors into alpha, where alpha is the power of the primes. Okay. Here. So we can use this property because this property is if and only if. You see that? This property is if and only if. Both way it is true. If this property is satisfied, then the number is m Zumkeller number. Or if the number is m Zumkeller number, this property is satisfied. Okay. So now we'll come back here. Now what is 2 square into 3 into 5? Can you one of them tell me what is the number of positive divisors for this number? Can you tell me what is the number of positive divisors for this number? 2 square into 3 into 5. I given one simple technique. No, what is that? For each of the prime numbers, see the power number. For the first, what is the first prime number? 2. 2 power is what? 2. Add one number. 2 plus 1. What is the next prime number? 3. 3 power is what? 1. Add one number. 1 plus 1. What is the next prime number? 5. 5 power 1. So add one number. So what's the answer? 2 plus 1, 3. 1 plus 1, 2. 1 plus 1, 2. Is it this number is divisible by 4? Is it this number is divisible by 4? Then yes. So this is divisible by 4 means this number is a m Zumkeller number. This number is m Zumkeller number. Like this, we are assigning the labels for each of the vertices in the other places, so that the label of each of the edge connecting those vertices will be a m Zumkeller number. There is an algorithm there, because randomly if you do it, it will be very strained. Just given a graph with 7 vertices. But imagine in a real life situation, you are modeling some relationship between the various communication systems, where we have thousands of nodes, thousands of vertices, and millions of edges are there. How can you assign like this by trial and error? So I have provided one algorithm for this, how to correctly give the assignment of labels for each of the vertices in the twig graph, as well as how to work it out the labels for the edges. Okay, so the algorithm later, if somebody is interested, I can share it later. Okay. This is a graph, what I said, hem graph. Okay, what do you call hem graph? It's an extension of a wheel graph with some pendant edges. Okay, so there is a wheel base is on wheel graph, and whose circumference vertices are attached to one more vertex outside. And there also we can assign such a labels for the vertices such that it obeys the M Zumkeller labeling. Okay. And this is another example of labeling a sunflower graph. This graph we are calling a sunflower graph. And this is a graph obtained as a, there is a product called Corona product. Corona product of two graphs. One is flower graph, the other one is we are calling path graph. Here in Corona product, what we are doing actually, suppose if we consider a flower graph, suppose flower graph has 4 vertices like that, then P3 has what, 3 vertices. Okay, now you attach a 3 vertex graph to each of the vertices of the FL4. That means what? Suppose FL4 has 5 vertices, means you take the 5 copies of P3, then attach with each of the vertices of the flower graph. Such a graph we are calling as what? Corona product. For Corona product also we are able to establish what? M Zumkeller labeling, and that is explained in the screen. I think the font size is less. I can share it later, those who are interested. Okay. So as a conclusion, labeled graph is a topic of current interest for many researchers, as it has a diverse applications. And we have explored our graph labeling using some special numbers that are represented by legendary or Jacobi symbols and M Zumkeller numbers. And already in the literature we can find out the applications of that Jacobi symbols based, that is actually Jacobi and legendary symbols are defined in terms of quadratic residue. There is a concept of what? Quadratic residue. So that quadratic residue, only here we are terming as what? Square residues. This square residues find numerous application in various fields, especially in the complex digital signal processing also, we find some application here. And investing this labeling in the other class of graphs, graph operations and applications of this labeling further are all future works. Okay. So these are the references for the papers on what? Square residue labeling and M Zumkeller labeling. So now it's open to all. Any questions? Some of them already raised their hands. I just want to address for them. Yeah.
Okay. Okay, thank you. Okay, thank you, Dr. Kamaraj, for that brilliant presentation.
Okay.
Now we are open for Q&A session.
Yeah.
Please feel free to ask regarding the presentation. Anyone? Any question from the floor?
Good afternoon, Dr. Kamaraj.
Good afternoon. Good afternoon.
I'm Adiba. Thank you for sharing about graph labeling.
Welcome, welcome.
Yeah. I would like to ask about the application. Let's say we would like to apply the Zumkeller numbers, right? So if we want to, my question is, are there any, for example, if we want to apply these Zumkeller numbers for labeling, Are there requirements or restrictions that must be satisfied? Let's say we want to apply zoom calendar numbers for labeling
the edges.
complete
Yeah,
graph or
yeah.
wheel graph and so on.
Yeah.
Will there be
These are
conditions
the
that must be
what
complied?
restrictions, what I have mentioned as in the labeling definition, that itself will take care of all the restriction. So you don't expect any other restriction. Okay, so I can just once again I'll go back to the definition. The restriction here. Yeah, the restriction is mainly what we have to work it out the labels of the vertices in such a manner that the product will give rise to what? A zoom color number. Okay. So that means what? We have to identify an algorithm only. So that depends on the graph, the algorithm differs. It's not for all the graphs we have a single algorithm through which we are getting the labels for the vertices and labels for the edges. So that task is a slightly, we have to be careful, or we have to work more. Okay. So for depends on, suppose if you are representing a network by some graph. Okay. For that particular network, you have to devise an algorithm to assign the labels for vertices and edges so that M-zoom color labeling is possible. So it is not that for every network we can apply the same algorithm. For each network, we have to identify one algorithm. So I think that is a part we have to work it out. So am I answered for you?
Yeah. Actually, to be more specific, the question, let's say, it depends on N. Yeah, you have yeah, for example, just now we have complete graph KN. Yeah, so let's say we want to know whether we can apply it for any N, any wheel graph of any complete graph KN.
Yeah.
Is there any particular condition for the number of vertices?
Yeah. So what you are asking actually is, suppose here I given my results for some other graphs like a wheel graph and twig graphs like that. Okay. Suppose if you consider a twig graph on any vertex, here in my example 7 vertices twig graph, the path containing 7 vertices I have shown. But in real life situation, if you have a twig graph where the path contains 1000 vertices, for that also the algorithm what we have devised for P7, that will work. Okay, for any twig graph, the algorithm will work. But if you go for a complete graph, you have to devise one new algorithm. Okay, so for that algorithm, if you able to successful for finding the algorithm for a complete graph on any n vertices, you can apply it for any number of vertices.
Okay. Thank you for Doctor. Yeah.
Yeah. Welcome.
Okay, anyone else? Anyone else to ask? Feel free to ask question.
May I ask one question, please?
Sure. Yes.
Doctor, I'm just wondering on motivation to choose this Jacobian de Legendre symbols. Because it is related to my second question, which is your proofs are given in some examples. Do you have any theoretical proof which based on
theoretical? Yeah, I have a theoretical
based
proof
on Legendre symbol or Jacobi symbols.
Right. I have one of the results in the presentation itself. I have mentioned one of the results what we have proved. It is not existing in the already literature.
In fact, you are using that labeling you are using for classification of graphs, right?
Yeah.
For classification.
It's actually labeling. Yeah. So we are actually saying what our graph can admit such a labeling. What labeling? Square residue labeling or zoom color labeling. Okay. So we are classifying that certain graphs are admitting such a labeling. Okay.
What's the
certain
point
graphs are not admitting.
What's the point of labeling? Is any application in the classification or in graphs or what?
Yeah, actually, we have numerous applications for graph labeling itself. But particularly for this square residue graph, which will uses a concept of square residues or quadratic residues, which are particularly applicable in the prime factorization theory as well as cryptography. Okay, in recent time I have seen one article which is also involving the quadratic residue concept in crystallography. It's a very entirely different area where the crystallography also can be studied using the quadratic residue or square residue concept.
Okay, thank you.
Okay.
Okay, anyone else?
Can I have a question?
Yeah, sure. Yeah.
Good afternoon, everyone. Thank you for your speech and presentation. I would like to ask a simple question. You are working in integer numbers, so in the set of integer numbers, is it?
That means integers you're saying. Okay, yeah. Actually, I'm not very specific to that. Graph theory research, okay, graph labeling and fuzzy graphs and graph domination, those kind of various field I'm working on that. But in this particular research, I'm connecting the number theoretical results to label our graph. Okay.
Oh, okay, thank you.
Okay.
Okay, and anyone else? Any more question from the floor? Okay, I think that's all, Dr. Kamaraj. Thank you for the presentation. Thank you so much.
Sorry, Dr. Rini. I think we have one question here from.
Oh, okay.
Yeah, you can carry on. Yeah. Yes.
From the chatbot, Dr. Rini.
Yeah, they're asking on optimization problem, how to apply.
Also, optimization problem.
Afternoon,
Can you read the question?
Dr.
I think they have
Kamaraj.
texted
So we
some
have
message.
question here. The question is, can I use graph labeling in finding the best route for
I think your voice is slightly breaking, ma'am. Can I once again repeat the question? The audio is not clear. Audio, I'm not able to get it actually.
Dr. Kamaraj, the question is, can I use graph labeling in finding the best route for optimization problem?
Sure. Because nowadays itself, some of the applications of the graph labeling we are using in the optimization problems only, especially the communication networks at all. Okay, so surely we can use graph labeling concepts. We can definitely use for what communication problems, especially in identifying the shortest route or shortest path connecting the two end vertices. That at all, the labels will definitely play a vital role. Yeah.
Okay, any more question from the chat bar or from the floor? Okay, I think that's all. Thank you once again, Dr. Kamaraj, for your presentation. Okay, thank you.
Okay, thank you.
Now, before we ended our webinar session, let's have a photo session. So I hope everybody can switch on their camera for this session. Okay, thank you for your cooperation, Dr. Hazwani. You can take the picture from the floor. Please switch on your cameras so that every picture can be taken. Okay, Dr. Hazwani, are you ready? Have you taken the photo yet?
Sorry, Dr. Kamaraj, please
Yeah.
unshare your slide.
Yes.
Yeah, shall I unshare my, do you want to unshare it? Stop share it?
All right. Okay, everyone ready?
Okay, so 1, 2, 3, smile. Okay, Dr. Rini, taken.
Okay, thank you everyone. Okay, before that, let me put the attendance. Okay, I already put the link on the attendance for those from WebEx, and for those from YouTube, let me share my screen first. Okay, this QR code for those from YouTube, but you can also from WebEx also can just scan the QR code, and it will directly go to the fill in the form, and automatically you'll get your e-certs through your email. Okay. Okay, now we have managed to finish all the presentation by our both speaker, Dr. Harliza and Dr. Kamaraj. So on behalf of our College of Computing, Informatics and Media, KPPIM, University Tanjung UiTM Malaysia, and our speakers, thank you so much for joining us today, and have a great rest of your day. We look forward to seeing you at our next session, session 3. Thank you, everyone. Salam Ramadan to everyone who's celebrating, okay, who are fasting. Okay, thank you.